Welcome to the cosmic stage. Today, we're embarking on an extraordinary journey to explore one of the most spectacular events in the universe, supernovae, the explosive deaths of stars. These breathtaking phenomena are not merely fireworks in the night sky, they are monumental cosmic events that profoundly shape the universe as we know it. To truly appreciate supernovae, we must delve into the intricate life cycle of massive stars. Stars are born in nebulae, vast clouds of gas and dust, where gravity pulls matter together, igniting the fusion process that brings them to life. For millions of years, a star like our Sun undergoes nuclear fusion, converting hydrogen into helium in its core. This process generates immense energy, creating a balance between the outward pressure of nuclear reactions and the inward pull of gravity. As these stars age, they embark on a remarkable journey of transformation. In massive stars, fusion progresses through stages, from hydrogen to helium to heavier elements like carbon, oxygen, and finally iron. Iron, however, represents the end of stellar fusion. While lighter elements release energy when fused, iron absorbs energy instead, leading to a crisis in the star's life. Without the outward pressure to counteract gravitational collapse, the stage is set for a dramatic finale. When the core of a massive star reaches a critical mass, approximately 3 times that of our Sun, the gravitational force becomes overwhelmingly powerful. This initiates a catastrophic collapse, causing the core to implode at astonishing speeds. Within mere seconds, temperatures soar to millions of degrees, and the core reaches a density comparable to that of an atomic nucleus. This rapid implosion is followed by an explosive rebound of the outer layers, a cosmic eruption known as a supernova. The energy released during this event is so immense that it can briefly outshine entire galaxies, lighting up the cosmos in a dazzling display of brilliance. Supernovae can be classified into 2 primary types, Type 1 and Type 2. Let's first explore Type 1 supernovae. These occur in binary star systems, where a white dwarf, the remnant core of a low to medium mass star, accumulates material from a companion star. This accumulation happens gradually as the white dwarf siphons gas from its partner. As it gains mass, the white dwarf approaches the Chandrasekhar limit, about 1.4 times the mass of our Sun. When this limit is reached, the pressure and temperature in the core soar, triggering a runaway nuclear reaction that leads to a catastrophic explosion. The resulting Type 1 supernova completely obliterates the white dwarf, releasing an energy output equivalent to that of billions of suns. The explosion is so powerful that it can be detected across vast cosmic distances, allowing astronomers to observe it from Earth. The luminosity of a Type 1 supernova can briefly outshine its entire host galaxy. This remarkable brightness provides a valuable tool for astronomers, as these explosions serve as standard candles for measuring cosmic distances. By analyzing the light curves of these supernovae, scientists can determine how far away they are from us, aiding our understanding of the universe's expansion and the mysterious force known as dark energy. Now, let's shift our focus to Type 2 supernovae. These events mark the explosive deaths of massive stars, those that are at least 8 times more massive than our Sun. After exhausting their nuclear fuel, these stars face an inevitable collapse. The core implodes under the immense gravitational pressure, resulting in an extraordinary transformation. As the core collapses, temperatures reach staggering levels, triggering the fusion of even heavier elements in the remaining layers of the star. This fusion process produces elements such as silicon and sulfur, which eventually culminate in the creation of iron. However, Once the core is primarily composed of iron, fusion stops, leading to the core's catastrophic collapse. The outer layers of the star, once supported by the outward pressure of fusion, now plummet inward before rebounding explosively. This explosion expels the star's outer material into space at incredible velocities, often exceeding 10,000 kilometers per second. The shock wave generated by this cataclysmic event can also interact with surrounding interstellar gas and dust, creating stunning nebulae that are visible across the universe. The beauty of supernovae lies not only in their explosive nature, but also in their role as cosmic factories. During these violent eruptions, the extreme conditions facilitate nucleosynthesis, the process of creating new elements. Heavier elements, including carbon, oxygen, and even the heaviest elements like gold and uranium, are formed and expelled into the interstellar medium. This enriching process is vital for the evolution of galaxies and the formation of new stars and planets. The remnants of supernovae, often seen as stunning nebulae, offer a wealth of information about stellar evolution and the conditions of the early universe. Take the Crab Nebula, for example, which is the result of a supernova explosion observed by Chinese astronomers in 1054 AD. This nebula is not just a visual marvel. It acts as a laboratory for studying the remnants of stellar explosions. As we observe these remnants, we gain insights into the dynamics of supernova explosions, the distribution of elements in space, and the interactions between the remnants and the surrounding interstellar medium. For instance, the shock waves from a supernova can compress nearby gas clouds, triggering new star formation, a process known as triggered star formation. This illustrates the cyclical nature of stellar life and death. Around the globe, astronomers are dedicated to observing supernovae with powerful telescopes, both ground-based and space-based. The study of these cosmic events is crucial for understanding the dynamics of our universe. For example, the discovery of dark energy, a mysterious force driving the accelerated expansion of the universe, was significantly advanced by analyzing the light from distant Type Ia supernovae. By comparing the brightness and distance of these supernovae, astronomers can gain insights into the history of the universe, revealing how galaxies have evolved and expanded over billions of years. Each supernova we observe serves as a cosmic time capsule, offering a glimpse into the past. The light from these explosive events may have traveled for millions or even billions of years to reach us, allowing us to witness outcomes of processes that shaped galaxies long ago. Supernovae are not merely astronomical curiosities. They are vital to our understanding of the cosmos and the history of the universe itself. Moreover, supernovae play a significant role in shaping galactic dynamics. The shock waves generated can compress surrounding gas clouds, instigating the formation of new stars. This process highlights the interconnectedness of cosmic events, where the death of one star gives rise to a new generation. Some scientists theorize that supernovae could even regulate star formation within galaxies. By injecting energy and momentum into the interstellar medium, supernovae can disrupt the gravitational collapse of nearby clouds, thereby controlling the rate of star formation. This regulation affects the overall structure and evolution of galaxies over billions of years. The elements produced in supernovae are distributed throughout the universe, contributing to the cosmic web of matter. These elements are essential for the formation of planets and life. Without the heavy elements forged in the hearts of stars and distributed by supernovae, planets like Earth and the life they support would not exist. As we explore the cosmos, we uncover the profound connections between stellar processes and the conditions necessary for life. Each supernova enriches the universe, allowing for the complex interplay of matter and energy that shapes the galaxies we observe today. Supernovae are not just cosmic events. They are fundamental players in the grand narrative of the universe. They remind us of the dynamic and ever-changing nature of the cosmos, where creation and destruction coexist in a magnificent dance. Each explosion is a moment of cosmic rebirth, shaping the very elements of which we are made. As we continue to explore the universe and unravel its mysteries, supernovae will remain a focal point of research, illuminating our understanding of the cosmos and our place within it. Thank you for joining us on this explosive journey. Don't forget to like, subscribe, and keep your curiosity alive. Until next time, keep looking up, for the universe is filled with wonders waiting to be discovered.